Section: Introduction. In this section, we discuss how adapting large, pre-trained models to specific tasks through fine-tuning is an efficient way to create tailored models. The most straightforward method is to fine-tune all parameters of the pre-trained model using data from the target task. However, as these models become larger, full fine-tuning can become difficult and costly. Recently, we have seen the rise of parameter-efficient fine-tuning (PEFT) methods, particularly low-rank adaptation (LoRA), which allows us to fine-tune with significantly fewer parameters. While LoRA can achieve performance similar to full fine-tuning, we question whether the solutions produced by these two methods are truly the same. Full fine-tuning treats every parameter as adjustable, whereas LoRA updates a weight matrix by expressing it as the product of two smaller matrices. Although this approach has proven effective, we still lack a clear understanding of how it achieves results comparable to full fine-tuning. One possible explanation is the intrinsic dimension hypothesis, which suggests that the updates from fine-tuning have a low intrinsic rank, indicating that LoRA might find a solution similar to full fine-tuning. However, previous studies have noted differences in how LoRA and full fine-tuning can alter the way a neuron processes its input. Additionally, LoRA has struggled to match full fine-tuning performance on more complex tasks, such as code and long-form text generation. This raises the question of whether these limitations reflect LoRA's capacity to adapt to specific tasks or if the two methods inherently learn different solutions. In our paper, we demonstrate that full fine-tuning and LoRA indeed learn different solutions, which can be identified by their unique spectral properties and generalization behaviors outside the target task. We observe the following. 1. LoRA and full fine-tuning generate different parameter updates, with LoRA introducing intruder dimensions, singular vectors that are nearly orthogonal to those in the pre-trained weight matrix. In contrast, fully fine-tuned models maintain a spectral similarity to the pre-trained model without these intruder dimensions. 2. LoRA models with intruder dimensions tend to forget more of the pre-training distribution and show less effective continual learning compared to fully fine-tuned models. Even when they achieve similar accuracy on the adaptation task, LoRA models perform worse outside that task's distribution. However, higher-rank LoRA models, which perform equally well on the adaptation task, resemble fully fine-tuned models more closely in these aspects. Even full-rank LoRA models forget more of their pre-training distribution, indicating that LoRA faces the same trade-off between expressiveness and generalization. 3. Even if a low-rank LoRA performs well on a target task, a higher-rank approach may be more beneficial. We find that our low-rank LoRAs fit the downstream task distribution as well as full fine-tuning, but using a higher rank leads to better generalization and adaptability. To leverage these higher ranks, the LoRA models must be rank stabilized. In summary, we explore the methods of fine-tuning pre-trained language models, highlighting the differences between full fine-tuning and LoRA, and how these differences impact performance and adaptability. Section Summary. In this section, we discuss the differences between full fine-tuning and low-rank adaptation, LoRA, in adapting large pre-trained models, highlighting that while both methods can achieve similar performance, they learn structurally different solutions with distinct spectral properties and generalization behaviors. We find that LoRA models often forget more of the pre-training distribution and exhibit less robust continual learning compared to fully fine-tuned models, suggesting that higher-rank LoRA configurations may be more beneficial for generalization despite similar task performance. Section: LoRA variants. In this section, we explore various adaptations of LoRA. There are many methods that enhance LoRA's performance or memory efficiency, such as initializing with key components of the weight matrix, using quantization during training, adaptively assigning different ranks, or training multiple LoRAs sequentially. While we acknowledge these variations, we concentrate on the original LoRA setup as outlined in previous work, leaving a detailed analysis of these adaptations for future research. We find that setting the parameter alpha to twice the rank has been shown to yield better results for higher ranks, and we use this setting in most of our experiments. We also discuss the intrinsic dimension measure, which suggests that fine-tuning updates for pre-trained language models have a low intrinsic rank, indicating that only a few trainable parameters are needed to achieve near-optimal performance. This leads us to hypothesize that LoRA is effective because low intrinsic rank solutions exist. However, we note that no previous studies have compared the rank of weight matrices between LoRA and full fine-tuning on tasks where both methods perform equally well. Our findings indicate that LoRA tends to forget less of the previously learned information and resembles the pre-trained model more closely than full fine-tuning. However, some of our experiments show contrasting results, likely due to differences in the datasets used. We focus on models where LoRA achieves the same performance as full fine-tuning, allowing us to compare their generalization behavior at a fixed accuracy level. We utilize singular value decomposition, SVD, to analyze the changes fine-tuning makes to pre-trained weights. SVD allows us to break down a matrix into components that reveal how fine-tuning alters the model. We measure how well the singular vectors from LoRA and full fine-tuning align with those from the pre-trained weights using cosine similarity. Our observations show that the singular vectors from LoRA fine-tuned models generally have lower similarity to pre-trained singular vectors compared to those from full fine-tuning. We introduce the concept of intruder dimensions, which are singular vectors from the fine-tuned weight matrix that do not closely match any pre-trained singular vectors. We define these formally and provide examples. Our analysis reveals that LoRA fine-tuned models contain high-ranking intruder dimensions, while full fine-tuned models do not. To quantify intruder dimensions, we compute the SVD of both pre-trained and fine-tuned weights and measure the maximum cosine similarity of the top singular vectors with pre-trained singular vectors. We find that LoRA consistently has more intruder dimensions, especially at lower ranks, while full fine-tuning maintains a closer mapping to pre-trained singular vectors. We also examine how intruder dimensions evolve during fine-tuning, noting that they tend to increase in rank and change direction as training progresses. By adjusting the alpha parameter, we observe that setting it to twice the rank reduces the number of intruder dimensions and increases the effective rank of the matrices. Finally, we investigate how the size of the fine-tuning dataset affects the number of intruder dimensions. Our results indicate that as we train on larger datasets, more intruder dimensions are introduced, particularly for higher ranks. We conjecture that these intruder dimensions significantly impact the stability and performance of the model, potentially hindering its effectiveness outside the fine-tuning task distribution, a phenomenon less pronounced in full fine-tuned models. We will explore this conjecture further in the next section. Section Summary. In this section, we explore various LoRA variants that enhance performance and efficiency, while focusing on the original LoRA setup for our experiments. We analyze the differences between LoRA and full fine-tuning, particularly noting that LoRA introduces intruder dimensions in weight matrices, which may negatively impact generalization outside the fine-tuning task distribution, unlike full fine-tuning that retains the spectral properties of pre-trained models. Section: Behavioral differences between LoRA and full fine-tuning. In this section, we identify structural differences between LoRA and full fine-tuning and explore how these methods affect the behavior of fine-tuned models. Although we have observed that both methods perform similarly in distribution test sets, we want to see if these similarities persist across different distributions. We find that at lower ranks, LoRA tends to forget previous tasks more during continual learning. To investigate this, we train the Roberta model on a series of tasks in a specific order: MNLI, QQP, SST2, SIQA, Winogrande, and Fever. After completing training on each dataset, we merge the LoRA weights into the model and reset them before moving on to the next task, ensuring they are not influenced by prior tasks. After training on each task, we test the model's performance by retraining its classification head for each task separately. Our results indicate that while LoRA initially matches the performance of full fine-tuning, lower ranks of LoRA show a consistent decline in performance during continual learning. Notably, for the first three datasets, the performance of LoRA with a rank of 1 falls below the baseline established during pre-training. As we increase the rank of LoRA, we observe a reduction in forgetting behavior, making it more similar to full fine-tuning, especially on the MNLI task after continual learning. We also describe scenarios where LoRA forgets less than full fine-tuning, but the overall findings are complex. For LoRA models that achieve similar test accuracy, we notice a U-shaped trend that helps identify the optimal rank for minimizing forgetting of the pre-training distribution. We assess the performance shift of our fine-tuned models on their pre-training data and measure a pseudo-loss for all fine-tuned Roberta models across the datasets used during pre-training. Our findings reveal a U-shaped trend between full fine-tuning and LoRA with a rank of 768, indicating that a rank of 64 minimizes forgetting of the pre-training distribution. We see that both very low, rank 1, and very high, rank 768, ranks lead to more forgetting compared to full fine-tuning, while a rank of 64 results in less forgetting. Additionally, we find that setting the alpha parameter correctly is crucial for model performance. We continue our investigation by using a fixed alpha of 8 instead of scaling it with rank. Our experiments show that LoRA models, regardless of rank, forget more of the pre-training distribution and previously learned tasks during continual learning, particularly for the first 2 datasets. This suggests that using an alpha of 8 leads to solutions with more intruder dimensions, resembling the behavior of low-rank LoRA settings. Section Summary. In this section, we investigate the behavioral differences between LoRA and full fine-tuning in continual learning scenarios, finding that while LoRA initially matches full fine-tuning performance, it tends to forget previous tasks more significantly at lower ranks. Our results indicate that optimal rank settings, particularly around R equals 64, can minimize forgetting of the pre-training distribution, while both very low and very high ranks lead to increased forgetting compared to full fine-tuning. Section. Why do intruder dimensions exist? In this section, we explore why intruder dimensions arise. When we add a random vector to a pre-trained matrix, it introduces an intruder dimension. To understand how new singular vectors can be added by LoRA, we look at the mathematical conditions that lead to their creation. Specifically, when we compare the singular value decomposition of the updated matrix, the pre-trained weights plus a scaled random vector, to the singular value decomposition of the original matrix, we find that this update is likely to create an intruder dimension because the random vector is almost orthogonal to the existing singular vectors. We also note that LoRA and full fine-tuning have different update rules, even when using the same training examples. LoRA employs a larger learning rate and projects gradients into a low-rank space, which creates conditions similar to our earlier example. Regarding the product parameterization in LoRA, we find that multiplying matrices can enhance their spectral differences, often resulting in a lower effective rank. To investigate how the product of 2 matrices affects the introduction of intruder dimensions, we initialize one matrix with all singular values set to 1 and keep it fixed while tuning the other matrix. This approach is valid because we have observed that tuning this second matrix is more significant for generalization than tuning the first one. Our findings indicate a notable decrease in the number of high-ranking intruder dimensions when we only tune the second matrix compared to the standard LoRA method, where both matrices are trained separately. This suggests that the matrix product in LoRA plays a crucial role in introducing intruder dimensions by amplifying the spectral differences between the 2 matrices.